Okay, so what I want to talk to you about is our long-term vision we've had for what we call data-centric systems. So we've been looking out and what we call our Vision 2023, looking at the architectures of the future and really trying to put together where do we think things are going, how these structures are going to play out, and how they're going to influence the algorithms and stuff that we see today. So one of the things that we start with is we see data as the basis of all the values. So we start with the data, looking at that corresponding, how does it move around the system and stuff. So there's a large amount of it. There's a lot of dark data that's, data that, hasn't been really processed and used and stuff. And so we see it in all sorts of industries. So we're looking at across all the different things that IBM works on to see where we're going to use the data and how we're going to really derive the value out of it. So we want to look at the structures and the computational systems to really drive that value as you store your data and really want to process and gain insights into it. So this leads us to how we're looking at our high performance computing. So that the roots of our organization stuff are in HPC, but we're also moving forward into what we call our cognitive systems. And we see a merge between these different systems of the capabilities and the desires of them in our operating. So one is a convergence of the capabilities, but we also need one system to handle the wide, diverse set of applications and desires as we span all the way from our business analytics all the way to the oil and gas, social analytics. But there's a lot of common properties of these kind of computational systems as we move forward. So this is a key part of our strategy, is make sure we're spanning this wide diversity of needs. So there's always this part you say, okay, what are the challenges we have? Well, we've all been sort of talking lightly about the end of Moore's Law, but it's actually occurring in a lot of different ways. One is, well, there's a strong demand for stuff. This is great. There's a lot of demand for data. It's growing exponentially. The computational needs are growing exponentially. But unfortunately, our tools that we have to work with are starting to limit ourselves. So there's, you can look, we've seen it, first thing to hit us was the clock rates on processors. That rolled over and that limited some of our capabilities. But you also look at disk and I/O performance capacities, and they're not keeping up with where we're going. And then if you look at the network, well, they're growing, which is great, but are they growing fast enough to really meet our needs? So there's a confluence of a lot of things starting to, dig down on slowing us down and moving forward in different areas. I think a little more disturbing is actually when people talk Moore's Law, haven't really talked about the economics, but this is one view that actually things started at 28 nanometer, that actually the price flattened out. This is the price per transistors delivered to you. So there's still value in pushing density and getting more and more transistors on the chip, which will drive value. But the problem is if your price per transistor really isn't dropping, that really is slowing down the economics. When we talk about exascale and all those flops that you need, delivering those flops it's going to be really hard to do it cheaply as this curve sort of plays out. Now there's lots of technologies that are under development. We go through a long list of saying what people are working on. There's a lot of great work. But unfortunately, all these sort of seem stagnant at 5 to 10 years out. Everybody says, okay, here's some great technology. And then, where are the areas that are really bringing these technologies in? You'll see them more coming in from the consumer line of people pushing technologies. And that's where we try to keep an eye on. Where's the high volume markets? What's really going to drive these technologies? Because they're really, really expensive, first to develop and then commercialize and bring to bear against some of these problems. So as we see all these challenges, we are turning to architectural concepts and new ways of forming your systems to drive up efficiencies and really take on some of these problems. So we look at our landscape. So we see there's a new world of HPC that's spanning everything from, what are we getting out of the application performance? We see it's a key aspect looking at workflow optimization. We're looking at the analytics and how the analytics are driving simulation. We'll talk a little bit about smart computing and where we think things need to go there. And then as the data grows and grows, there's a lot of management resources that need to be put in play. We really need to make the data and its management a very integral part of the system, and as we move that forward. And as we look at more of our systems, not just using AI, but using AI to drive the simulations and some of the computation to get higher value out of the work we do. So part of the other challenge we have is, as I said, going over the diversity, and I like using this chart just to sort of emphasize, what's really going on in a computer system compared to what people sort of look at when they first want to buy something. So LinPack has been used for a long time to say, here, let's measure, how good is a machine and stuff. We sort of did a plot of what LinPack and what it looks like, and then we looked at diverse applications, and you can see those lists here if you can read the small writing, and you can see the different colors that really are stressing the systems in much different ways than a benchmark really might sort of lead you to expect. So this is why it's important for us to really look at real applications, real diverse loads that we put on our system, and make sure that they're actually providing you the value that you need, and you're not just looking at one benchmark that's not really representative of most stuff that they'll actually run on the machine. So the other thing as we looked, is we sort of saw from Alan was talking about diverse needs of computation. So, one of the problems is there's a certain efficiency you're going to get out of the CPU. If you look at other heterogeneous elements like the GPUs, other vector processing type of structures, they're more specialized. And with that more specialization, you're going to get more efficiency in your compute, which is great. But the problem is that they're specialized and they don't handle that wide diversity of workflows and applications that we saw in the previous chart. So as we embrace these specialization stuff, we want to do this in a way where we can actually deploy this and bring it easily to people's use. So we're taking a look at something about looking at the diverse compute capabilities we have. On the left side here, this is what we see is running on a big, strong core when you're doing analytics and stuff, and very complex kind of interactions with the computer and the algorithms. On the right side is what is really good with highly parallel systems that you might find in a GPU and stuff. And we see that there's different needs pulling on both sides of this. So we need to make systems that actually allow you to do both of these workflows at the same time and rebalance yourself between these specialized engines and the general purpose engines as they're specialized for both of these pieces of work as we move forward. So the other part that we look at is the workflow. So one thing is take a look at the sort of the specialized pieces. So, well, gosh, you might look at the full wave migrations and the piece in the middle here and say, well, that's where I spend all my time. Let me make sure that that's fully optimized, which is really important. But we want to make sure that as we want to look at the whole workflow as you collect your data, how you're bringing it off the Gulf of Mexico, put it on ships, transport it somewhere, and then start a long process of going through the data, filtering, sorting it, looking at statistics of it before it feeds into the really computational pieces, and then moves on to interpretation and analysis of that data as it goes forward. So we see that we look at this holistically as a full process, and we want to make sure that we're optimizing all the different pieces of this as we move forward. The other really important part of this is our data storage techniques and stuff. So we have a lot of work we have going on our spectrum scale devices. We've had things like Netezza, where we're actually doing a lot of pre-processing and work in the data as it lives on the disk or flash, wherever it is in the system. So we want to make sure we do smart analysis and stuff in our storage systems, but also make sure it's a repository of data that can be easily accessed from all the different parts of the workflow as things are moving forward. So this is a critical part of our systems and looking how it also ties together. So as we first started looking at our sort of our approach to the efficiency and stuff, it all gets back to the chart you saw earlier from David about how expensive it is to do different pieces of work, from the computation to actually the data movement. So we look on the top right here as traditional computing systems, and this is sort of the way I look at it, saying, okay, you start and you say, okay, you start with a page fault in the storage system, you start bringing in a main memory, you finally gets into your caches, then you can finally start doing some processing, you'll do a bunch of work on it, and then you'll eventually push it back up to storage. So there's a lot of work in prepping the data and moving it through the memory system, which is all consuming energy and time as it moves through the system. So as we started our data-centric principles and stuff, we said what we really want to look at is look at all the different elements of the storage of the system and the different levels we have, and say what is the appropriate type of processing that we should put on each one of these levels. So as you're working on your data, as you start with it from the furthest pieces out of the storage, what do you do out in your database operation? What do you do for query filtering? What is the appropriate type of processing to put there? Then as we look at into the storage class memory, and when we talk about storage class memory, we're thinking about non-volatile flash or future PCM, something like that. Where do we get into our file system operations and start doing data transformations? And then even as we bring it into main memory, we want to look at how do we do streaming operation, key value operations on the DRAM. And then finally, you can get it to your processor where you have a cache backing you up and doing some of those type of operations. But we're really trying to shift the thought from, oh, let's suck everything into the processor and do the work, as now let's process it effectively at each of these different stages. And then how do we control such systems? So one way we look at doing this is we break this up into our 3 layers. So the top layer we call D0. This is our highly dense computation that could either be our GPUs or our CPUs doing low-level work and stuff. We have what we call our D1 level that's in the middle. This is where we'll put our storage class memory and really put the bulk of your working set in the computer system, and then backing it by storage in those different computations. So what we did is we highlighted the different colors, the blue being the highest compute stuff, down the red the storage, looked at the different pieces in different workloads and activities that you need to do through it, and sort of broke it down into which are the appropriate places that you should do this type of work and where in the system it should be processed. So we're sort of starting at this level, deeply understanding the workflows, where the processing needs to be, and making sure we're supplying systems to handle all this diverse set of work that needs to be done across the entire workflow. So as we set forth on this, we developed a number of different principles to sort of work this. So the first thing we have is worrying about that energy component, which was much more than the compute, and to start with minimizing the data motion. So we know moving it is expensive, and our basic mantra is put the data appropriately in the system where it should be, and then have the appropriate processing power there to do the work that you need to have done. So this sort of taking this in a holistic approach is how we're going to minimize our data movement and make sure it's properly positioned in the system. To enable that, we need to have compute in all the different levels of the system, as I was showing you in the previous picture, so that we can enable these sort of activities. The other part that we need to work on is modularity. So there's a lot of diverse applications. People are going to need different ratios of these different activities and such. So we want to make sure that first, the systems, as you acquire them, are composable in different ways, and you can acquire them in different ratios. And also, to drive up utilization, we want to make sure that you're able to, at runtime, actually go after the resources you need to solve your different problems that you have. And then our other principle is to look at application usage, what is people are going to do in the future, and actually make sure that we run a holistic design approach so that as applications and other applications are being developed, we're developing architectures, hopefully, that are suited to those needs that we see coming in the future. So, as we look at things, we have to be sort of shooting out, 6 years out in front of where we think the algorithms and what people are currently doing today to hopefully design the systems of the future that are doing that. So one of the things that is important for us in IBM is to make sure that we have architectural leverage and places to innovate on that, and that's why we keep our own architecture, like the Power architecture, alive and well in our system. We work with a lot of partners because we know we can't do all this work, so we leverage other people in the industry doing GPUs or other people doing storage, other places, so that we can make sure that we have a wide inventory of places to drive our innovation. So along the OpenPOWER, so we have what we call an OpenPOWER Innovation Center. So what this allows is we've opened up the architecture so people can easily license it in a very economical way, and we want to collaborate with lots of people across the industry. And so as we've opened this up, we've got hundreds of people that have joined the OpenPOWER Consortium, and we are working in a very effective manner to start providing you different solutions as we move forward. And so after we've started with this OpenPOWER, one of our initial partners was NVIDIA, Mellanox, and other ones. So we developed our first generation sort of roadmap, taking us through our different systems. So we started opening up with what we call our CAPI interface on Power 8, and then enabled FPGAs and other people to put innovative solutions in with our servers. Recently announced is what we call our Power 8 with NVLink and Pascal GPUs. This allowed a lot more bandwidth in this innovation to get to the GPUs and extract a lot of the performance, and this is selling well. It's a code name under Minsky. You might have heard of this program. And then looking forward to what we're doing with our Coral is a Power 9. This is our next generation CPU. This will be coming out this year, and we have an enhanced NVLink attaching to the Volta GPUs coming out of NVIDIA. And the first step, actually going into this step, will be actually opening the coherency model for the GPU. So as we work on providing that flexibility and stuff in the systems, the first step we had here was really to open up the bandwidth and a bigger spigot to get to the GPUs. And in this one, we're flattening out the address model that'll allow new programming models and easier way to access this performance through our Witherspoon node here and how we're going to move forward. So this has been sort of shown publicly, and we've got our big wins with the Coral, so with Oak Ridge and Lawrence Livermore Laboratory going to be acquiring these systems next year, and that installation will be occurring later this year. We also have a strong partnership with STFC, where we're doing a lot of research on big data and looking at different science technologies and such through some of these other facilities. So, people have been looking at these kind of technologies, embracing them, and we've got a lot of financial support moving these initiatives forward. So, the other thing that is, as we look at, is very important is the programming approaches and how do we take on some of this work. So we've started initially with most of the GPU, we think of it as sort of an accelerator approach, and we call this sort of an offload model, and you take some, you have some data in your CPU, you move it over to the GPU, you do some work on it, you might have to communicate back, move it back and forth, and that's what we call a sort of a copy-only model, and you don't really have any coherency between them. But as we move forward, and I was saying we want to move to an address space that's shared between the CPU and the GPU. This will allow a much higher degree of sharing between the different components and making the programming models a lot more accessible to people. So one way we were trying to show how this would work is if you look at sort of the traditional way in the upper left, you might say, okay, I have a CPU on the bottom and I have a GPU at the top. The data in your working set would be kept in the CPU, and then you type a piece of work, you offload it up to the GPU, and when it's done, you pass it back down. Well, you could also flip that around and say, well, maybe the GPU should be the master. Maybe it owns the data. It does a whole bunch of work, and once in a while, it needs a CPU as an accelerator, and you pass it back and forth. What we're pushing forward is to say, what we really want is a peer processing model. So the appropriate type of processing you do on the CPU, or the appropriate processing you do in the GPU, it's a much more natural thing, and you can pass the information back and forth between the two. And we allow this because we have the coherency built up between these two memory subsystems so that there's equal addressing accessibility. So an object on the CPU, an object in the GPU, they look equivalent, and you can have natural programming approaches to this and not be burdened with just copying data around all the time. So as we look at that, so that's driving some of the programming strategy that we have for OpenPOWER, and that's leading us to OpenMP. So we're looking at these different needs that we have, from easy porting to the high-level abstractions and what we want to do with it. So here's our wish list of sort of taking these on, making sure we have higher level abstractions of the different types of needs here. We need to have performance portability. This is sort of mandated through the industry to make sure people don't get stuck on one architecture or not. So we need to make sure we have performance portability across our different systems. We also need to make sure that we have continuity with what's going to go on in the future with different types of systems. So we're fully embracing these open standards and moving ourselves toward more portable type of computing models as we move forward. So one example we have is how we got performance out of our system. So the first bars over here on the left were basically saying, let's take code that was unoptimized and really kind of had poor affinity to an acceleration type model. That went through sort of a significant porting effort, and we got a lot more performance out of it. So we optimized the code, we got a lot more usability out of the GPUs and stuff, and there was a fair amount of work that went in the code. We also took pieces of code that were actually good code affinity to the acceleration, and also did, a lot of porting, and that brought us to even higher performance. So then we said, well, let's just, and this is not really a controlled scientific experiment, but at least it was a try at trying to get a feel of how hard it is to program up some of these different systems. So on the one on the right, actually lower is better, and the dark blue bars indicates somebody that was, somebody that came in, a grad student working in OpenP, and he started working on a problem. And the green bar was represented by an experienced CUDA programmer, came in working on CUDA, and gave him the same problem to solve. So they had about 2 weeks to work on it, and you see that the blue bars are actually performing better than the green bars. And the basic reason was that the person could get the OpenMP running and getting stuff going, and then he spent the rest of his time actually doing optimization and work. Whereas on the CUDA side, it was basically all the effort was just to get it working, and once you got it working, that was kind of the performance he had, and he didn't really have time to go in and tune it. So this is where it gets into, as we get to a model where we improve the productivity for programmers and such, we want to apply that actually shows up in performance, because your time to solution and how you can extract performance out of these systems as things change and stuff really get better. So then I want to talk a little bit about our cognitive solutions and some of the structures that we're looking from that, and what we're sort of learning as we get more and more in depth into providing solutions on the cognitive side. So one of the things that, that we're talking about is saying, really work smarter and not hard on the problems. And part of this is the floating point work you really don't do is the fastest stuff you have. So, we're looking at different calculations. This is some SOAP simulations and where the things are breaking down. And it was sort of looking at, where can we actually really put the work on the areas that you need to do. So there was a certain part of the matrix and this triangle and those things that are highlighted that we put all the execution time on, and we really sped things up. Another way to look at this is saying if you're doing some material science simulation and there's some sort of terror is occurring, you want to put all the processing power where the new work is going on. Now, if you take, going back to your old world of MPI, and if you break everything down into very structured, block synchronous type of operation, it's very hard to dynamically shift the work around to where the center of activities and areas of interest are. So we really want to look at providing programming models and such that you can rebalance those boundaries dynamically at runtime and really improve the efficiency. So this will be sort of a basic tool that we want to provide in the architecture, that you can more dynamically go there and address, and put your processing power where you need to put the work. And then over time, what we want to do is drive that from AI and other cognitive works to help drive where that happens. So we look at these workflows and look at the different phases and do that. And usually there's one pass going through the different parts of the data and stuff. And what we want to provide is saying, okay, what we really want to do is do more times doing preparation, minimize and measuring stuff so that you refine it. You can prepare the simulations and do this work a lot more smarter as you go through it. So we want to get in sort of the role of what do we do in looking at the entire workflow and using some of this AI and cognitive stuff and say, how can we do this, looking at this at a high level to really address some of these problems. So, this sounds good and it's futuristic in some sense, but what we need to do is make sure we're providing the architectural elements and structures so that this work can be experimented and explored on. And part of that's going after the addressing models, the structures of our systems, to make sure that this is easy to do over time, or at least reasonable to approach. Oh, I have a click through. Okay, let me get them all up. So one thing that we're looking at is, oops, let me go back, is looking at how we're going to look at clouds and moving ourselves also into the cloud environment and their sensitivity to that. So it's very important for us to make sure that we're providing a lot of computer services initially through the cloud and other public type of mechanisms to get there. But we also see that it's important that people keep their machines and activities local and stuff. So part of what we want to do in this hybrid world is make sure that the software stacks and other things that we have in the cloud are also available to you in a more private on-prem type of mechanism, or making sure that we're providing you a mechanism if you have a number of private on-prem stuff and you have an offload capability or excess capability that you can seamlessly move it to the cloud and also do some of your computation off-board. So we want to make sure that sort of a seamless environment and you have a lot more choice as this world sort of evolves and more and more work will be done in the cloud compared to just private control of the work. So one of the things we're working on is this portfolio of products we have and making sure that they have this sort of capability. So we have what we call a software-defined infrastructure portfolio. starting from our IBM Spectrum computing and Spectrum scale. So that's our resource management, how we allocating work across the system. Spectrum scale being our storage capabilities, our GPFS type file systems. And then that goes down to our cluster foundation with OpenStack and XCAT. And then that's using that to provide capabilities and support for all the different hardware mechanisms and system pieces that you have down below, whether how that's allocated across all these different types of systems. So one thing that we're working on is creating a reference model for the oil and gas solutions of saying, what are these different pieces, and making sure that we're coming up with a portfolio of these different software stacks and hardware standards so that as the world moves forward in this area, we can provide you the reference model for these different types of activities. So we sort of started off, working with our basic, HPC systems. We're focusing on performance and the traditional type of aspects on it. Today we're more working on data analytics, the full workflow performance, and our heterogeneous type of compute elements. And that represented in our systems, our Coral systems with Sierra and Summit going out there, and our Witherspoon node that was based in Power 9 and the Volta GPU. So as we move forward, we're going toward these exascale systems. We're going to improve our cognitive capabilities, integrating other technologies. So we know there's other technologies of the future, like our Synapse capabilities, our quantum computing. As we have access to these technologies, we're making sure that they're going to be seamlessly fitting into our systems as we move forward, and you have access to those kind of technologies. And we'll allow this, on-prem or in the cloud as we move forward. So basically, we look at our data-centric systems. It's the ability to generate, access, manage, and operate at ever larger amounts and varieties of data in this, evolving technical systems that we have, and that's moving forward. So we see that, the value is in the data, and we need to extract insights and enable real-time and predictive type of analysis coming off that data. We see that there's a lot of disruption going on, especially as data is becoming the central critical natural resource that we have to deal with. And as we look at our data center innovations, we're looking at the architecture for our design, our module building blocks. We're always looking at hardware technologies. We have new innovations that are coming along. And of course, we need a software ecosystem and other things to support this more and more complex world as we move forward. Okay, that's where I am.
I have time for a couple of questions. There's one here. You have them lined up today, don't you? That's okay. We need to have questions.
I know that IBM was working on developing a lossless seismic compression algorithm on the FPGA. Mm-hmm. Can you comment to that?
I'm not super familiar with that one, but in our different portfolio of technologies, we'll definitely be supporting FPGAs and other accelerations. I'm not very clear on that piece of work, but we'll definitely be supporting of that as we move forward.
Bill, microphone is coming.
You had an interesting concept of moving the data to the different elements of, or moving the processing to the different elements of data. And I wonder if you can comment on how you see that really working. I'm thinking of the end user is going to pre-process seismic data. They're going to do the first steps of migration and model building. They're going to do all these things on different kinds of computers, appliances. How do you see IBM? What do y'all think?
So we look at this as a heterogeneous system that's got a uniform system structure, resource management, and all that. So you're not going to be saying, what we don't want you is saying, oh, let's move from one system to another system, right? Let's just say you're doing some simulation and modeling, and then you want to do some visualization. Right? We think that the hardware we have can actually do both of those well. So we don't want to spend the time moving from one system to the other. We want you to actually say, let's keep that in the SCM. Let's keep a working set there. So as you move from one phase to another, then you have the architectural and hardware capabilities to do those different phases, but not be discrete appliances and stuff. Now they are specialized. That's what I mean. They're heterogeneous, but they're not appliances like they're separately managed and resourced, and you got to move things from one world to another. We want to keep sort of a seamless, common ecosystem and embracing those different elements.
Please join me in thanking Jim McGann.
Thank you.